Okay, thanks. All right, well, first of all, thank you, Rosh, for hosting the mini symposium. And I'm Jostein Barry-Straume, and today I'll be talking about physics-informed neural networks for PDE-constrained optimization and control. So I think we've already overviewed SIAM and pins, but another way to think about scientific machine learning is sort of this synergistic feedback loop. So you can use machine learning to discover physical laws, but at the same time, you can use physics to enforce some sort of given physical law. And often this creates a synergistic feedback loop that forms the basis of scientific machine learning. And like we've seen, an example of that are pins. So we've already covered pins, but on the top row we have physics only, and that's great, but that only works if you know the laws of the system that you're trying to model. On the other hand, we have data only, and that can work well too, but as you see, the network is unable to predict beyond the observations that we have. So that really means that it hasn't really learned the problem. So the solution is you can combine both the physics and the data to predict out-of-sample situations. And oftentimes, to do that, you want to have a network that outputs a prediction of a physical quantity, which you then use to take multiple second order and mixed partial derivatives. And you use those derivatives to enforce the physical laws of whatever you're trying to model. So, a fundamental problem is designing optimal control policies that steer a given system towards a desired outcome. And a classic example is lunar landing. So we will have a lunar lander. We want to land it on the moon, but we want to use the minimum amount of gas to do so. So to do that, we have a multi-stage decision process which sequentially makes numerous decisions over time and space. This in turn creates a sequential repetition of decisions, and that becomes a control policy. That control policy enacts decisions to maximize or minimize an objective. And like I said, that objective could be minimizing gas, but it also could be an example of the cart pull. Say you want to minimize the amount of force that the cart is moving left or right. So this is important because SIAM can replace traditional numerical methods because they offer a mesh-free approach via automatic differentiation, and they also break the curse of dimensionality. So the existing applications of pins to solving optimal control problems usually either feed control data to a pin, so they already have pre-computed controller data, and or they're using an external controller in conjunction with the pin. Which brings us to the first paper we're talking about is open loop control pins. So why should you care about what I'm talking about right now? Well, the novel results presented in this work is a one-stage framework which simultaneously learns both the dynamical system and its respective optimal control. So it doesn't rely on a priori controller data, nor does it rely on an external controller. So what we have is a framework that solves PDEs in continuous time and space. And this is important because it avoids huge systems of nonlinear equations created by two-stage approaches. Which brings us to our methodology. So in order to accomplish that, we first have to formulate a PDE-constrained control problem. So there's a lot going on with this slide, But the best way to think about this is imagine you have an autonomously driven car, and you want to drive that car from point A to point B using the most efficient amount of gas. And so the system state of this car is represented by Y. And the control signals that you're sending to this car are represented by U. And those control signals could be how you're steering the wheel, or pressing the brake or accelerator. And in turn, lambda, or the adjoint, is the response of the car in response to the control signal. And this is important because we're going to solve the PDE-constrained control problem using the Lagrangian written in terms of the adjoint. So it's there's a lot going on, but we are going to attain a local minima using first order optimality conditions. And so we're going to talk about this in a couple of slides, but we're going to equip the pin with the loss function with these optimality conditions to ensure that there is an optimal control. All right, so this is the architecture of the control pin framework. It probably doesn't look like a normal network, but that is because we want the network to, since it's simultaneously learning the system state, the control, and the adjoint, those all need to be outputs of the network. But we also need the network to learn them in a certain order to enable the automatic differentiation to compute second and mixed order derivatives to equip its loss function to find the optimal control. So obviously the T and X are inputs, time and space, get fed into a given number of hidden layers. You try to predict the system state, which is passed further into the network, which then tries to learn the control signal, which is passed deeper into the network, along with basically a skip connection of the system state to learn the adjoint. So we have the architecture. How do we train the model? Kind of already talked about some of this, but we're constructing a network, and we have the inputs and outputs. We're taking the derivatives with respect to the inputs to equip the model with basically the heart of the framework is the loss function shown in equation 4 in step 3. So there are 4 components of this loss function. The first component is the least squares error of the system dynamics. That's pretty simple. It's just the MSE of the predicted system state versus the actual system state. The second term is the evolution of the forward system dynamics. So this means what is the car, like how is the car responding to how aggressively you're driving it. And in turn, the third term is the evolution of the adjoint system dynamics, which is the response of the car in response to the control signal. And lastly, we have the control optimality equations. These are basically KKT conditions to ensure that we are reaching some sort of minima. After that, it's pretty standard. We just have a fancy loss function now. We're going to train it until convergence. We use Atom. You don't really have to use Atom, but that just worked the best. So we now have our heuristic to train it. So let's get a simple toy problem. This is a very basic ODE control problem. And the important part is that it gives us an analytical form of the system state, the control, and the adjoint. So we now know after 300 epochs of training that the network has converged on the analytical solution. Okay, so we have the toy problem that's demonstrated success. So now we're going to increase the complexity with a one-dimensional heat problem. You can think of this as a one-dimensional steel beam that's being heated or cooled such that at a given final time it has the desired heat profile that we're looking for. And this is showing, so the main takeaway is that on the bottom row, we have the final time. And at the final time, we have reached the heat profile that we're looking for. But a curious observation is that the network found a more optimal control signal than that of the analytical control. But we were, at the time, we were kind of like, okay, that's interesting. So we made sure we validated it. So we plugged back the analytical control and the learn control into the dynamics, and they match basically exactly. But the learn control is more optimal. So we just did a little bit further validation. We just ran it 10 random seeds. The network converges roughly to the same control signal and also onto the analytical heat profile. So there's just a little bit further validation that it actually is doing what we want it to do. So now we're moving on to a two-dimensional unsteady problem. It's actually three-dimensional because there is a time component, but it's a 2D predator-prey problem formulated as a reaction diffusion problem. This is best thought of, to me, think of Yellowstone Park as a Cartesian grid. At the end of a certain time span, we want, say, 4 population of bison to be present in the park. So in order to reach that goal, we need to introduce predators or wolves into that park at different points of time and space. So we're controlling the final population of bison at the final time. And this is basically the mean squared error of the prey and predator populations as we approach the final time. You can see at time 3/4 of the way towards the final time on the top row, it's not really well formulated, but as you get closer and closer to the final time, we basically have 0 error. This paper is available on arXiv as a preprint. We encourage you to read it in full. We would love it even more if you cited it. So please give it a read. All right. So now we just discuss open loop paper or open loop pins. So we're going to go even further and talk about closed loop control pins. So the results presented in this paper are a 2-stage framework for closed loop control problems, and it's solving the learning task of the optimal cost to go. And it's important to note that the network weights are warm started on suboptimal LQR cost to go data. And then after that, the optimal control is calculated via automatic differentiation of the learned optimal cost to go. So this framework solves PDEs in continuous space in the context of an infinite time horizon. Okay, I'm not going to go like too deep into optimal nonlinear control, but this is a really good overview of that topic from Steve Brunton's video lecture series. I encourage you guys to check it out if you haven't. But basically, the goal of optimal nonlinear control is to design a control signal U of t that follows a state x, which is the magenta squiggly line, such that we're minimizing a cost j. So in the context of the car, it would be the literal cost to go of that car. So we're doing this using the Bellman optimality, which in turn is using the HJB equation. And I guess it's important to note that V is a value function. In the act of minimizing that value function is the cost to go itself. So in the context of this paper, we are specifically doing the time invariant case with infinite horizon. And that's important to note because if you look at his slide, there's a starting time and an ending time. But in our case, the integral goes to infinity. So it's an infinite horizon. And this is important because we have that cost to go function, which is being learned by the network. And so the principle of optimality shows that the optimal costate lambda corresponds to the gradient of the optimal cost to go function. And this is really important because the network is learning the cost to go. And then once you have a learned optimal cost to go, you can take the derivative of that to get to the lambda. And the lambda is used to calculate the optimal control signal. And specifically, the problem we're doing with this paper comes from Dirk's 2010, which is just a nonlinear, unsteady two-system state equation in the aquamarine box. And it makes it really easy to validate because that paper already has the analytical form of the HJB, which is pretty hard to formulate sometimes. So now we have, moving on to the architecture. It's pretty straightforward, like the architecture itself. You're feeding in the system states. It's passing through 3 nonlinear activations. It's predicting on the cost to go. But the important part is that we had to warm start the weights of the network on suboptimal LQR cost to go data because the problem itself is so nonlinear that the network just gets lost trying to find the global minimum. But once we have the weights warm started, we then hot swap the loss function from just a standard MSE loss function to the loss function shown in equation 13. And that guides the network to the actual optimal cost to go. And so this is validating the results. So with no control signal, the brown and purple lines are the 2 system states. And so with no control, those are unbounded in time. But then once you introduce a control signal, which are the analytical control are the red and green boxes, and the learned control are the red and green lines. And you can see they exactly match, and the error of those dynamical systems are shown on the right. It's a little cut off, but those errors are small. So yeah, this is important because it's showing that the optimal cost to go is found, and it's able to stabilize the system. All right, so then I just wanted to show the sort of the 3D landscape of the mean squared error of the adjoint. And this is a really good example of, I don't know if you guys have worked with pins, but there's always this tension between the interior and boundary points. And you can see that the higher errors are occurring at the boundary points. And again, same thing with the control signal. Yeah, I mean, it's just, I think, a nature of pins. So yeah, and then this is showing the 3D landscape of the Hamiltonian. The analytical solution is a flat plane on 0 on the y-axis, and this is also a good example of why further methodologies of resolving the tension that pins have between enforcing the physical laws, the interior and the exterior points. So some challenges, lessons learned from the closed loop portion of this paper. This was intended to be a novel ensemble control framework, but in order to do that, we needed to make sure that one single framework worked by itself. We found that the solution to the time invariant affine HAB is not unique, so it was extremely difficult to guide the network towards the global minima without warm starting the weights, which meant we fell into the prior approaches categories of using a two-stage framework and also using an external controller. So I don't know if you guys remember, but the open loop paper completely avoided those prior approaches, whereas this framework currently is falling back into those categories. And also, the early implementation of this worked on the carpole problem, but only when it was linearized and only when it was low angle approximating, which just isn't good enough. In my experience, pins have been very popular since 2019, but a lot of the problems that people use to demonstrate success are linear and very fundamental. So this paper was an attempt to tackle a non-trivial problem. And that's it. Those are my citations.
Thank you very much, Jostein.